All right, guys, it's time to talk about the very first lab that you're supposed to do in the program. And I told you in the syllabus videos that this laboratory experiment is really pretty basic. And there's nothing probably that you're going to learn in this lab that you've not learned in a previous laboratory course before. The issue with this one, though, is to take a look at the laboratory notebook, and that's really where our focus is going to be. But at the same time, I need to give you some background information about the pH of sodium benzoate. So, we need to talk about the structure, we need to talk about what it does, we need to talk about the things to look out for, and that way you have enough background information to really understand the entire purpose of the lab experiment and why you're doing what you're doing. So, with that said, let me flip this over to my handy dandy notebook. All right. So sodium benzoate, we're going to have to start there at least. All right. So we're going to first draw the structure of sodium benzoate, and we're going to talk about what this structure really means, and we're going to talk about some of the important aspects that I should take away from this organic molecule. So benzo in chemistry typically refers to the benzene ring. Now, not every time, but I'm probably going to find a benzene ring about 99% of the time when I see that word. So what is a benzene ring? Well, a benzene ring is this six-membered ring in chemistry that kind of circles all the way around. And then in the center, there are three sets of double bonds. So we see a double, single, double, single, double. Now, sometimes I get a little bit lazy as well as others, and instead of writing the double, single, all the way around, I just simply draw a circle in the center, and that represents the same thing. The reason is because I had two choices here, and these two choices, I could have drawn the double bond here at the top right, or I could have started it here to the right-hand side, and that would have been the double, single, double, single, double. And these two kind of never tell the full story because these are what we would call resonance forms, okay? So the resonance forms, the real structure is a hybrid between the two. So it's a little bit of double, it's a little bit of single orientation, but it's all the way around the molecule. So because of that, they typically will make a hybrid, and the hybrid part of the molecule, the double bond could happen here, so we'll draw a dotted line. And the double bond could happen there in one form, and here in one form, and there in one form, and here in one form, and there in one form. So that dashed line basically represents that double bond could be found, or partial double bond could be found everywhere where that double bond is located, which is all the way around the molecule. And that's why we draw a circle in the center, because that circle represents that double bond can be found everywhere, or at least partial double bond characteristics can be found everywhere. Okay, so that's a little bit about the benzene as part of the benzoate structure of sodium benzoate. Now, that's not the only thing, all right? So up here at the top, we're going to draw another bond, and that bond is going to be attached to a carbon, and I'll typically draw a little dot there, just so I don't get confused. And off of that carbon is going to be a double bond that connects to an oxygen, and then off of that carbon is also another oxygen that carries a negative charge. And that negative charge is going to cause us some problems, but that also causes the chemistry of what goes on, because that's a full-blown negative, and it's going to attract positive things to it. Well, this is the benzoate piece that we are referring to. All right, that's benzoate. right there. Now, the sodium is straight from the periodic chart, and that sodium is going to be an Na+. And you know what? Good news, because that sodium carries a positive charge with it. So here, this sodium is going to hang out with that negative charge on that oxygen, and we have sodium benzoate, and that is the structure for sodium benzoate. So the issues here is, number one, some of the questions that we can answer. Is this thing polar? So, meaning, does it have a charge? Is there a charge distribution in the molecule? Is one part of it having a charge and the other part of it pretty neutral? And the answer is yeah, because we see a sodium with a positive and an oxygen with a negative. Nowhere else do we see full-blown charges like that, right? So the molecule is going to be classified as polar. So the next question, will it dissolve in water? And the question is, yeah, because it's got charges. It's polar. So remember, like dissolves like. So if I have a polar solvent, it will dissolve polar compounds. And this is a polar compound because of those full-blown charges that it has on the molecule. That's being dissolved up in water if I add water to it, and that's basically what you're going to be doing in the laboratory. So this stuff should dissolve on you, okay? Some other things about the structure. Number 3, it has a formula weight, and the formula weight is 144.10. Now, how do we get the formula weight? That's gram per mole. What I do is that I go to each one of these carbons. There's a carbon here, and a carbon there, and a carbon here, and a carbon there, and a carbon here, and a carbon there. I add up the weights of all of those carbons. There's a carbon here as well. I add that one into the mix. Then I add the 2 oxygens from the periodic chart. I add those weights up. And then each one of these will have enough bonds to have 4. So there's hydrogens here, right? So this carbon has 2 bonds, so that also means that there's 2 hydrogens that are there. And this one has 2 bonds, so I need 2 more hydrogens. This one's got 2 bonds, so I need 2 more hydrogens. This one, same story, 2 more hydrogens, right? And this one, same thing, 2 more hydrogens. Now, if you did that, I've led you into a mistake deliberately that most people do. And the reason is because they look at this structure and they go, oh, that carbon only has 2 bonds because there's one to the left and one to the right of it. That's wrong. And the reason that it's wrong is because you've got to keep in mind this circle in the center. That circle in the center means that there's double bond characteristic all the way around. So let's say I go and look at this resonance form of benzene. This carbon does not have 2 bonds. It has 3. There's 2 to the right and 1 to the left. So that means there's only 1 hydrogen that comes off of that thing, not 2. And the same thing's going to happen to this one over here. There's 2 to the bottom and 1 to the top. So there's already 3 there, and it can only have 4. So there's actually only 1 hydrogen that's there. So that's one of the ways that people get screwed up when it concerns these structures. So I need to go back and I need to erase all of those extra hydrogens that just went on that molecule, because each one only has 1, right? So there's 6 hydrogens that point off of the ring in total, not a total of 12. And this oxygen doesn't have any because there's free pairs of electrons that make it happy. You'll learn about that in organic chemistry. 2 bonds, 2 pairs of electrons makes oxygen happy. The same thing's going to happen here. We just have some extra electrons that are hanging out. And this carbon in the center has 4 bonds in total. 2 to the left, 1 to the right, 1 down below. So the formula weight's 144.10. I've taken all the carbons, all the hydrogens, all the oxygens, and I've added them all up. The melting point of this thing, the melting point is going to be 410 degrees Celsius. So if I ask you to do a melting point of this in the laboratory, I want you to look at me and I want you to say, you're crazy. You don't know what you're talking about. You need a break. You need a vacation. Because there's no way that we can get a 410 degrees Celsius melting point with the equipment that we have in the lab. Now, why is this the case? Well, it's a salt. Most salts have very high melting points. Okay, that's kind of the tendency with a salt. So salts typically have massive melting points that are associated with them. And the reason that this is a salt is because I see an Na plus and then a negative piece. It's an ionic compound. A positive and a negative. And they're getting held together by an ionic bond. And that's an ion. Positive, cation, negative, anion. Sodium chloride is the same way, right? Okay, well, here's the thing. Sodium benzoate, a little bit about it. Well, number one is that it's commonly used as an ingredient in the food industry. And the reason that they use it is it's classified as a preservative. Now, not only is it used in the food industry, but it's also used in the cosmetic industry as well. Okay, so what is a preservative? Well, it kills bacteria. I can make a product, I can put it on the shelf, and it will stay longer on the shelf or in your refrigerator because I've put a preservative in it. It preserves the integrity of the food or the cosmetic that I sell to you. So, for instance, if I buy a loaf of bread, the reason that the bread stays good for a couple of weeks is because there's preservatives in it. If you made that bread at home, it probably would not last as long. So if you're really worried about preservatives, you're probably shopping at Whole Foods or you're shopping at somewhere like Trader Joe's where they limit the preservatives that are found in their food product. Now, this is only one preservative that people can use out there in the field. There's tons of other ones, but this is just one of the many variations that I could use in the product assembly. Okay, so sodium benzoate is not only just a preservative, but it can also increase the acidity of foods. And this kind of is related to killing bacteria because a lot of bacteria, they hate acid, they hate acidic environments, and because of that, it kills them out. Well, sodium benzoate kind of does that job as well. So if I'm making something that's acidic, and that could be something like soda. If you ever measure the pH of soda, you probably will be scared. It is classified as an acid. Jams are the same way. Salad dressing, a lot of those, especially if they're the oil and vinegar base, are going to be acidic. So sodium benzoate helps out the acidity for that reason. Well, there's a lot of things about preservatives. There are a lot of hot topics that go on when it concerns sodium benzoate. And one of the things is that, oh no, I don't want to eat it. You're putting chemical in my food. That's really what these people are saying. And some of these people, they have the right to kind of complain because they are putting chemicals in your food. But at the same time, a lot of these have been targeted as safe and as effective. And there's no way that you can get around it. If you're going to be a no preservative type of person, good luck. Your life is going to be very difficult. We're all going to die. So why make your life miserable trying to figure out what to eat and what to drink because you're always looking at the ingredient label to see if there's a preservative in it or not, right? Okay, so here's the thing. The FDA has stepped in. And the FDA you will hear a lot about. Some good things, but mostly bad things. And the FDA has took it upon themselves to give companies a kind of a threshold. You cannot put this much sodium benzoate in food product, because if you do, then this violates our terms and you cannot sell it to consumers. And the cap that they have put on it is 0.1%. And it's 0.1% by weight. Okay, so that means if I have a 500 milligram sample of food product, the FDA will allow a company to have preservative up to 0.1% by weight of sodium benzoate. Only sodium benzoate. Hint, hint. So I would take 500 milligrams and I can multiply it by 0.001, right? Because that's 0.1%. So that means I need to take it out of percent if I'm going to multiply it. It's like taking 25% off. You don't multiply by 25. You multiply by 0.25. That gives you the total discount if you're a sale shopper or a clearance searcher, right? Same thing's going to happen here. 500 milligrams times 0.001. And that's going to give me 0.5 milligrams of allowable sodium benzoate that can be put into that food product that I'm getting ready to eat. All right, well, that seems kind of low, right? A half of a milligram, that's not even a speck. The next time that you're in the laboratory, go in, look at a half of a milligram and see if you can actually weigh it out. You're going to have a difficult time trying to do that, I guarantee you. All right, so the FDA did step in. The FDA does control sodium benzoate a little bit, and because of that, we get some thresholds that we need or that we could be concerned with, right? Now, sodium benzoate, how does it do its job? Right? What happens when it goes into a food product? Because that's really what all of this is concerning. So let me clear this out. And I'm going to take sodium benzoate. Remember, it's this benzene ring with a circle. And then here I get a double bond O and a single bond O. And all of this is basically sodium benzoate. There's my Na plus and my O minus. Okay, well, companies, how do they make this? The sodium benzoate that they're going to use in their product. Where does it come from? Well, where it comes from is something called benzoic acid. And benzoic acid is the same benzene ring that sits down below, and it's got a carbon with a double bond here and an OH that's there. And this is called benzoic acid. The reason it's called an acid is because an acid gives up hydrogen. It gives up proton. Well, guess what, folks? We got a proton, and it's right here. And that can be spit out by benzoic acid if it's given the proper environment. Well, how do I give it the proper environment? Well, an acid typically reacts with a base. So if I bring in a base, then I could probably get this benzoic acid to spit off the hydrogen and allow me to do what I need to do with it. So NaOH is a suitable base. That's sodium hydroxide, people. That's good old-fashioned lye. And this is my base. And here is my acid, of course, because it says acid. If I give you a question on a test and I say, is benzoic acid an acid or a base? If you give me a base, I'm going to automatically fail you for the class because it tells you the answer right into the name. It's benzoic acid. All right, well, what we're getting ready to show is something called a mechanism. How do these two things react? If I was a company that needed sodium benzoate, then how on earth can I get this thing to do what it needs to do, and where do I start? Well, the companies can start with something called benzoic acid, and they can add a base to it, and a reaction is going to happen. But the reaction is going to require a little bit of attraction. One molecule has to be attracted to the other. And this is how it happens. When it concerns the sodium and hydroxide, the sodium is the positive area, just like it was in sodium benzoate. And the hydroxide is a negative area. This is a polar compound. NaOH is polar. And there's a negative charge that's here on the oxygen. That's where electrons are located. NaOH. I've got electron pairs on that oxygen. That makes it negative. Well, in the world of organic chemistry, what you will find out when you take those courses, if you haven't already, is that NaOH is the negative area. And when I show how these two compounds relate to each other, I'm going to start at the negative area and I point to the place that's positive on the other molecule. So NaOH is my negative, and I'm going to point to the positive piece, which is this hydrogen right there. Well, how did I know that was going to be positive? Well, that's the definition of the acid. The acid is going to spit out a proton, and that proton is a hydrogen, and proton is also positive. So the OH comes into the bar, and this OH looks around in the bar. Now keep in mind, it's coming with its boyfriend or girlfriend into that bar. Sodium's tagging along with it. It's currently in a bond. It's currently in a relationship. But that OH, it's sneaky. That OH has bar eyes. It's looking around to see if there's anything more attractive in the bar that it would like to take advantage of. And it finds it. It finds it in poor little O hydrogen. And that poor little O hydrogen is not going to see anything coming. And OH goes over like the big bully that it is. And it says, H, you're mine. And it rips the hydrogen off from that benzoic acid molecule. And then poor little benzoic acid. It's not benzoic acid anymore. Its partner has been ripped away. And now the only thing that we have is a double bond O and an O out here with a negative. And it goes boo-hoo-hoo in the corner. Well, the issue here is that the NaOH, this oxygen got a little bit greedy. And this oxygen, I'm going to just kind of draw this up here for just a second. NaOH, and now it's got an H from the sodium benzoate. This can never happen. When this happens, a positive charge gets formed and the oxygen bites off more than it can chew. It has an extra bond. Remember, always remember that in organic chemistry, oxygen is like it is in water, H2O. It needs two bonds, and that's it. The other, to make it fulfill the octet, comes from the electrons that are associated with the atom. So this has three bonds, one to hydrogen, one to hydrogen, one to sodium. And oxygen has to make a decision. It knows that it cannot have this kind of three-way going on. It's not going to work. So this oxygen makes the decision to say, sodium, it was good while it lasted. But guess what? Off you go. I'm kicking you to the curb. I don't need you anymore because I've got this hydrogen that I found in this bar when you took me out tonight. So thanks for making me understand my life is miserable. So off it goes, and H and OH go off and they make water. H2O. Well, this poor little sodium, it kind of goes off and now it doesn't have a bond anymore and it's positive. And now he's looking around in the bar and he's saying, what have I done? I should have even came out tonight and now my relationship is ruined. Tonight's miserable night. And then sodium looks over and it sees the benzoate. and benzoate's going through the same motions. I was just ripped of my partner that I had all this time. And they've got something in common. And they begin to hang out a little bit. And then a new bond gets formed. And this is the sodium benzoate. The Na plus and the O minus. Now, this will only happen if the pH level is proper. So on this arrow, I'm going to put pH. Because if I don't put enough sodium hydroxide into the system, this will not go forward. I need sodium hydroxide to be present, and I need it to be present in a large amount in order for it to bombard the benzoic acid and rip off the hydrogen from the molecule. If I do not put sodium hydroxide in there in a large amount, then the benzoic acid can take up for itself, and it's going to say, I don't think so, sodium hydroxide. You're going to go back, and you're going to sit in the corner, and you're going to mind your own business, and you're going to sober up. Because this is not going to work out. So pH is very important. And that's what you're going to discover in many of the chemistry reactions that go on. pH is going to be an important aspect to any reaction that goes forward. So we always want to check the pH of a solution. And we do this a number of ways. We can do a pH meter, or we can check it with pH paper. And that's what your lab is going to tell you to do in this circumstance. It's going to say, take this sodium benzoate, we want you to dissolve it in water, then we want you to acidify it, and we want you to go all the way down to this pH or lower. And you're going to be doing that with either a meter or a pH paper. Either one is perfectly okay. All right? So that's a little bit of background about pH, reaction, mechanism, the reaction between an acid and a base, and a little bit of structure property. So come back in the next video and we'll continue with our discussion of sodium benzoate.